Before we start the topic of alpha, beta, and gamma decay, which is collectively known as radioactive decay, and then radioactive decay can be of different types. Like I showed you in the video, it can be alpha decay, beta decay, and gamma decay. But the prerequisite is you must be aware of the alpha particles, the beta particles, and the gamma radiations. So the next thing, when a radioactive nucleus decays, its nucleus breaks up is broken down, is disintegrated, and emits an alpha particle or beta particle or energy and forms of a new element. For this one especially, only for alpha and beta. Yeah, for alpha and beta particle. Once you have the alpha decay or the beta decay, then the element is converted into a new element. What do we mean by this? I'll explain afterwards. So the element that was having there, that you were having there previously, which was going to have a radioactive decay, that element would be called parent nuclei. So let's say this is the element with plenty of the atoms. So once it decays and is converted into this one, let's say, with the emission of alpha particle plus energy, now this new atom would now be a different element. We call it a daughter nuclei. So before the radioactive decay, the element that you were having, the substance, the nuclei that you were having were parent nuclei, and after the process they are converted into daughter nuclei. Now let's take a look at the first one, the alpha decay. Now we study these decays in sequence: alpha decay, beta decay, and then gamma decay. So the most important thing in alpha decay is you need to keep it in your mind that in this process alpha particle is emitted. In this process alpha particle is emitted. So what we can write here is an alpha particle is emitted. I'm going to write down the symbol for the alpha particle. Alpha particle is emitted. And as it happens, as the alpha particle is emitted, according to the nature of the alpha particle. Now once again, what is the alpha particle? Alpha particles are the helium nuclei with atomic number 2. They have 2 protons. They don't have any electron because they are only the nuclei of the helium. So they have 2 protons. The proton number is 2. And the atomic mass or the mass number is 4. So 2 protons and 2 neutrons. And in the process alpha decay, because the alpha particle has been emitted, so the atomic number decreases by 2. So whatever the atomic number of your element was, whatever the atomic number of the parent nuclei was. After the alpha decay, there would be a reduction in the atomic number of that nuclei by 2 units. It would be reduced by 2. So the daughter nuclei will have a deficit of 2 protons. So atomic number decreases by 2. And what about the mass number? What do you think? There would be a decrement or reduction in the mass number as well. The reduction in the mass number would be equal to the mass number of the alpha particles. So there would be decrease in the mass number by 4. And plus, whether it be alpha decay, beta decay, and gamma decay, a high or a vast amount of energy is released. So let us take a look at the equations here. First, I'm going to write down the general equation. Let us explain the general equation first. So your element was X. This is your parent nuclei, and it is about to undergo the alpha decay. So let me assume the mass number and the proton number for this. Let's say the proton number is Z and the mass number is A. So after the alpha decay, one thing is for certain, that the alpha particle has now parted ways with this parent nuclei. Now alpha particle is no longer there. So as the alpha particle goes away, there would be a reduction of the atomic number and the atomic mass as well. So how do we define the alpha particle? We define it as the nucleus of the helium with the atomic number 2 and the mass number 4. So what is alpha particle? Nuclei of the helium. So what was the atomic number of the parent nuclei? It was Z. Out of that atomic number, there is now a reduction of 2 protons. So how many protons will you be left with? You'll be left with Z minus 2. Whatever the value of V is, there would be a decrement by 2 units. And then we have the other one. What about the atomic mass? So for the atomic mass, you see, the helium has, the alpha particles have the atomic mass of 4. The nucleon number is 4. So there would be a reduction of 4 in the atomic mass for the daughter nuclei. So the daughter nuclei would now be having the atomic number as A minus 4 and the atomic mass as A minus 4 and the atomic number as E minus 2. Okay, so let us consider some of the examples. That was the general equation, but now let us consider some examples. The most important one is uranium 92 and 238. So this thing, the uranium, is about to have the alpha decay. And they give you this thing, and they ask you to complete the equation. So what do? Well, if this thing is undergoing the alpha decay, as it is mentioned in the question, obviously they'll mention you what kind of decay this thing is going to have, or sometimes from the numbers in the equation you'll have to guess what decay is this. So it can go either way. The decay would be given, then you have to come up with the numbers, the balancing the equation, or sometimes the equation is given, from there you have to guess what kind of decay is that. So let's say the question is, this uranium isotope undergoes the alpha decay. Complete the equation. So if it undergoes the alpha decay, there would be the emission of alpha particle. What is alpha particle? Helium nuclei, He24, plus in all three of them, there is always a release of vast amount of energy. Plus, now this element uranium, after the alpha decay, would no longer be uranium. It would be converted into some other element, and we may not be able to come up with the name of that element, but what we know is the atomic number of this uranium, this element, would now be decreased by 2 units. So the new atomic number would be 90 for whatever the element is. Let's call it, for the timing, let's call it Y. So the new element then is Y, has the atomic number 90, and then the atomic mass would be decreased by 4 units, and the new atomic mass would be 234. And you can check the equation as well. What is the total atomic number on left side? 92. What is the total atomic number on the right side? 90 plus 2, 92. What is the total atomic mass on left side? 238. What is the total atomic mass on the right side? 234 plus 4, 238. Then we open up the periodic table and we try to find out what is the element for which the atomic number is 90. For the element with the atomic number 90 is none other than thorium. Thorim. How do you know? Are you supposed to memorize it? The answer is no. You're not supposed to memorize it, because in the physics paper you're not provided with the periodic table. So they'll probably write the element by themselves. They'll write TH here, and then you'll be asked to fill up these spaces. Fill up the atomic number, fill up the atomic mass. Or they'll just replace the word thorium, the element, by a general symbol, for example, Y. Alright, so they ask you these kind of questions. For example, if we take a look at this one equation over here on the left side. Okay, let's try to take a look at this equation. Now in this one, they'll probably ask you to complete the equation. The equation is written as it is. You're required to fill up these spaces. Okay, they'll probably underline these two portions. So you're required to fill up these two places. One over here, one over here. So what do we get on the bottom left corner of uranium? We need to plug the value of atomic number. So what should be the atomic number over here? 92, very good. And what would be the atomic mass? 236. And this is the standard isotope of uranium, the most important one, abundant one, which is found in the nature. This is the stable one. The other one, 238, is unstable, and this is precisely why it undergoes the radioactive decay. The next one that we have is the beta decay. So for this one, once again, you need to come up with the prerequisite, which is you need to understand what is a beta particle. Beta decay is simply a decay, a radioactive decay in which beta particle is released. So what is a beta particle? These are just the electrons. You can write it as E minus 1 and 0, like this. Or you can also write it as with the symbol beta, negative 1 over here and 0 over here. Okay, unless mentioned otherwise, unless they mention that you're having a positive beta decay. So in that case, it would be beta plus 1, 0. The atomic number, we read the atomic number first and then we read the atomic mass. So when the nucleus, an unstable nucleus, emits beta particles, Let me write it down. When the atomic mass remains the same, or the mass number remains the same. So mass number remains the same because the mass of the beta particle is negligible. It's not exactly zero, by the way, because even for the electrons the mass is not zero. It is like 1 over 1800 something, 1 over 1896 compared to the mass of the proton. Right? We say the mass of the beta particle is negligible. The important thing is about the atomic number. So here we are at this thing that the atomic number, so the atomic mass in the process of the beta decay does not change because the atomic mass of the beta particle itself is 0. So what happens to the atomic number? So can you guess what should happen to the atomic number as the beta particle is emitted from an unstable nuclei? So let us write down the general equation. So they'll give you with this thing. They'll leave you with this thing, and the question might be, complete the general equation for the beta decay. So the thing is, you know this thing, that this element X, the parent nuclei, is going to have the beta decay, so there would be an emission of the beta particle. So you write the beta particle on this side. So the beta particle has now been removed from the parent nuclei. What are you left with? You're left with the daughter nuclei, but now we got to fill up the proton number and the mass number. The mass number does not change, it remains zero. Sorry, it remains the same because the mass number of the beta particle is 0. And for the atomic number, it would be increased by 1. Okay, how? Because whatever the atomic number was previously, it was Z, and now -1 is decreased from Z. So you subtract -1 from Z, and subtracting -1 from Z would be written like this, and then mathematically this would be Z plus 1. So you're not subtracting 1 from Z, you're subtracting -1 from Z. So subtracting -1 means adding 1. So the proton number would increase, your element would get heavier. So we can take a look at some of the examples here, like for example this one. So they would ask you, they would give you the equation, and they would ask you to complete the equation. And also, for example, in the very first one you can add the energy as well, because be it the alpha decay, beta decay, or gamma decay, there would be a release of vast amount of energy as well. So you have this thing, carbon element, carbon nuclei, C614. So you see, this is not the standard carbon that you're familiar with, C612. C612 is a stable isotope. This one is not a stable one. This is a rare one. This is an unstable one. That's why you don't find it naturally. You do find it naturally, I mean, but it is very difficult to trace that one. The percentage availability of this isotope, the percentage abundance of this isotope is relatively low compared to the standard one, C612. And that's why it is unstable. It tries to stabilize itself to be converted into a stable daughter nuclei. And one of the ways is to have the process, or to undergo the process of radioactive decay. And they'll mention in the question that carbon 614, what kind of radioactive decay takes place for this one. So they'll mention like it is the beta decay. So we got to fill up these spaces for the proton number and the mass number. Mass number would remain same, 14 here and 14 over here. It does not change. But what about the atomic number? So atomic number would be written like this: 6 minus -1. So you're subtracting -1 from 6. So the atomic number would be increased by 1 if you have the beta decay. So in the beta decay, the atomic number is increased by 1, the atomic mass remains same, the energy is released. What is the similarity? Now, what is the similarity? If they ask you the question, what are the similarities in alpha decay and beta decay? The similarities are, in all of those, alpha decay, beta decay, gamma decay, radioactive particle is emitted. A radioactive particle is emitted. The other one, a vast amount of energy is released. Another one, atomic number decreases. Sorry, that is not the similarity, that would be the difference. So for the similarities, you have this thing, that the radioactive particle, be it alpha or beta, the radioactive particle is emitted, energy is released, a stable, relatively stable nuclei is formed. So these are some of these similarities. They generally ask for a single one, but you can write at least 3, so you can write, check out a single one or write anyone from these 3. So then you can check out the other examples as well. For example, the left one on the left side, cesium being converted into barium.